Right. So I don't know what it is. I'm just assuming there is one and that it looks like that one that I showed you before. I don't know what the values of those parameters are. Okay? All right. Now comes the magic. All right? Just repeated both equations here. This says the location of that point in the right frame in terms of the ray. This says in terms of the left in terms of the ray. Okay? But we know something about the relationship between a point in the right image and a point in the left if this were calibrated. Right? What did I know there? Well, that was last time. I know there's this thing called the essential matrix that would relate the ray to the point from the right frame to the ray to the point in the left frame. And the relation between them is called the essential matrix. Now, I don't know what the essential matrix is. Why? Because I'm uncalibrated. But I know there would exist one. Okay? So if I assume for a moment there exists one, then I can rewrite this equation like that. Okay? So all I did was substitute for the point ray in the right frame, which was from here, and I pulled that down into here. Okay? And do the same thing on the left. Copying that over, well, this is just matrix multiplication. I hope you all know that A, B, bracket transpose is just B transpose A transpose. If not, trust me. All right? So I can regroup using the associative property here such that here I have the transpose, and that's where this comes from that. Okay? And then what I can do is I can combine this whole thing, the K inverse, the intrinsics from the right transpose times E times K inverse of the intrinsics on the left. Remember, I don't know what they are, but I just know they exist. And I'm going to call that whole thing F. And when I do that, I end up with this beautiful, beautiful, beautiful equation. It just says that P transpose of the image point on the right, okay, so this is from the image now, times F times P in the image on the left equals 0. Okay? And this is a relationship between image points, which I can just write this way as P transpose F P prime equals 0. P being in one frame, P prime being in the other frame. That is the fundamental matrix constraint. That's what's going to allow us to solve for the relationship between one view and another. Given enough points that correspond, enough P and P primes that correspond, we're going to be able to solve for F. And once we do that, we know what relates the two images. Or this can just be written as P transpose F P prime equals 0. P in one frame, P prime in the other frame. It's the relationship between the points. Now, with this equation, I'm going to be able to do a lot of things. In a minute, I'm going to show you how we can solve for F. That is, if you give me enough points P and P prime that correspond, I'll be able to solve for F. But the other thing is, F is actually very powerful in terms of describing how the epipolar geometry works. All right, if you had actually been here while we were recording this, you would have seen that I just walked around the room 17 times trying to get my act together because I started to talk about this and my tongue just was but here goes, okay? Couple things, all right? So this relationship here, that's the relationship that happens algebraically between corresponding points. P and P prime are the image points of the same point outside in the world. Now, we remember from our epipolar geometry, so like that's over here, that if I've got some point, let's say it's right here in the image, I know that that's on this ray somewhere, and therefore that point must be on that epipolar line. That was the geometric constraint that we had derived earlier. So the P transpose F P prime equals 0 is the algebraic one. The drawings with the epipolar lines was the geometric one. But clearly they relate. So you'll remember from our projective geometry little tutorial that we said that the equation of a line, right, could be written a couple of ways. I'm going to write it this way. P transpose L equals 0, right? Remember, L was that normal to the plane, and all the points P had to be on that, in that plane and would be perpendicular to it. So notice, here we have P transpose, here we have this P transpose, here we have this L, here we have that L, here we have that FP prime, okay? These equal 0 is a line. That's the constraint that has to equal 0. What this means, and that's what's written here, is that this L, which is FP prime, is actually the epipolar line in the P image. Okay, so remember, I'm going to erase these, right? It's going to be multiplying a point in the P image. So L equals FP prime is the epipolar line in the P image associated with the point P prime. Also, just reversing this, that means that F transpose P is the epipolar line in the prime image, the P prime image, associated with the point P. All right? So what the fundamental matrix does is it gives us the epipolar line constraint between two views. So if I know what F is, I can compute the epipolar lines. In fact, you can just, for a given point, I just take F transpose P, and that's the epipolar line in the other image. And that makes sense because the F is what we said takes all of goes through the intrinsics of one, through the extrinsics, the intrinsics of another. And so the only thing I don't know for some point that I'm seeing in my left image is, well, since I don't know its depth along that ray, it has to be along this line. That was the geometry. So the fundamental matrix equation reduces that geometric constraint to an algebraic one. The great thing about video is you can go back and take a look at this. We'll also, in the class notes, there'll be some pointers to some texts where you can look at it and learn it from people who are way more articulate than I am. But that's the relationship between the fundamental matrix and the epipolar lines. Go back and look again. Do it again. Okay, so now you're here, and now you really got it. You understand it all, so you should really teach this class, but I'm stuck here on this side of the screen. You're stuck there, so I'll keep going. Okay, great. All right, now comes something cool. Again, a little bit complicated. We know that P prime is on the epipolar line corresponding to P in the other image. Okay, that's what this equation says, if this equation holds. But suppose P prime was on the epipolar line in the prime image for every point P in the original image. You might say, well, how could that be?
How could that be?
Thank you, Megan. Well, the way that could be is, suppose FP prime equals 0. Well, in order for a point to be on every epipolar line, well, there is only one point that's on every epipolar line. That's the epipole. So the way you find the epipole, given the fundamental matrix, is you solve this equation. And remember, there's two epipoles. There's the epipole in the original frame and the epipole in the prime frame. And so you just solve each of those equations, Fp prime equals 0 or F transpose P equals 0, and that identifies for you the epipoles in the image. So this F matrix is very powerful. It tells you everything you need to know, or almost everything you need to know, about the way the points relate to one another in terms of their projective geometry, and that lets you do things like find the epipolar lines and the epipoles. Pretty cool. One last thing about the fundamental matrix, and we'll look more at this later. The fundamental matrix is actually a 3 by 3, right? Because this is the homogeneous coordinate of an image point, so it's a 3 vector, okay? But I will tell you, we're going to show this in a little bit, that the F matrix is actually singular. And the reason for that is if it wasn't singular, it would map between points and points. But in fact, it maps between points and lines. So it maps from a 2D point to a 1D line. And that's what sort of requires that it be singular. We'll do a simple algebraic proof of it later. But it makes sense because when you give me a fundamental matrix and I give you a point, you can't tell me the point over here. All you can tell me is the line. So we go from something that has 0 degrees of freedom, a single point, to something that has another degree of freedom. And that's because the rank of the fundamental matrix is only 2 and not 3. Like I said, we'll show that to you in just a minute. So now that we have the fundamental matrix, well, so what? Well, as we said, it relates between the pixel coordinates in the two views. And it's much more general than the essential matrix because we've removed the need to know the intrinsic parameters. If you told me the intrinsics, okay, then I could figure out the rays that correspond. And if I know the rays that correspond in the 3D camera coordinates, I could compute the essential matrix. I could figure out the real rotation or translation. But if I have two arbitrary cameras that aren't even necessarily the same, the fundamental matrix allows me to relate them without worrying about the intrinsics or the extrinsics. So the bottom line is, if we estimate the fundamental matrix from the correspondences, then we can reconstruct our epipolar geometry without having to worry at all about the intrinsics or extrinsics of the camera. And that's what's done here. Here you see two pictures. I think this is also courtesy of stealing from Anders Isserman. And you have some pixels on the left and some pixels on the right, and then they were put into correspondence. The idea is I gave you corresponding points, and now the lines that are drawn on here, those are the corresponding epipolar lines. So in fact, if you take a look real quick, so you'll notice that, you know, here's a point right on the bottom edge of that window, and this line lands right on the bottom edge of that window. So these are corresponding epipolar lines. Any point that's along this line is also going to be along that line. Let's see, does that really work? Let's see, it goes across this chimney thing. Yep, there it is, right there. Okay, so that's finding the epipolar lines by given the correspondences through solving for the fundamental matrix. So let's work a simple example, all right, of finding the fundamental matrix. And a bunch of them out there. One that I'm going to show here is one that's a little bit different because it's not as sort of trivial. Here's the one of the two side-by-side stereo views. We'll do it a little different. And remember, a fundamental matrix gives a correspondence between any two views. It doesn't matter where the cameras are taken. Okay? So for example, my images could look like this. And you might say, whoa. Okay, you might not say whoa, because that would be only if you were born in the late 60s or maybe early 60s. But here I have a picture, and the white lines drawn on it are meant to be sort of nominal epipolar lines. I took a picture, and then the camera moves forward, and I take another picture. Can I do a fundamental matrix for that? Of course I can. In fact, that's what this geometry is meaning to show here. It's a little hard to see, all right? What I have here is that I took one picture, and my camera center was there, and then I take another picture, and my camera center is moved forward, and if you connect those and slice the image, those are the epipoles. So all the epipolar lines have to go through the epipole, and that's what this is showing you, right? The epipole is right in the middle of my picture. Here's not exactly in the middle. It's off to the top. It's actually to the side a little bit. I'll show you in a minute. But all the epipolar lines have to go through the epipole. And that's another way of saying is, you just think about that intuitively. If I move straight ahead and I'm looking straight, the points move along that diagonal out from the center. So that means that if you give me one point in the first image, it's going to be somewhere along that line in the second image. And how far it's along that line will be a function of its depth. Okay, because remember the amount that points move between one image and the next, function of depth, going way back, remember disparity. The closer something is, the more it'll be disparate. Something that's very far away, like the moon, doesn't change much at all. Okay, so they're going to move along these epipolar lines. So we're going to use this as an example because it'll be very clear whether you got the epipolar lines right or you got the epipolar lines wrong. So how do we compute the fundamental matrix from the corresponding points? All right, so here I wrote the fundamental matrix equation, and you'll notice that each point gives us one equation, and that's written here like this. So u prime v prime 1, that's the projective similarity of the point in the prime, times the fundamental matrix times uv1, that's the other point in the original image, equals 0. Okay? That's a single equation per point. All right? So copy it here, and I can just multiply this whole thing out, and I still have my one equation per point. And on the left-hand side, these are my knowns, right? So I take the u primes and the u's, or the v primes, or the v prime and the u, or just its individual, etc. And here are my unknowns, right? The unknowns are the elements of the F matrix. Okay? So 1 point, 1 equation. Well, I just collect n of these, right? N is however many number of points that I have, and then I'm going to solve the thing. So how do we do that? Well, there was originally something called the 8-point algorithm. It was done by, I think that was done by Christopher Loggett Higgins, and for a while it got sort of a bad